Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week, and I'm going to be talking about winds in the atmosphere, how they converge or come together or diverge and spread apart, and how that affects vertical motion in the atmosphere, which ultimately is what we want to assess, because when air rises you get clouds and precipitation. When it sinks you tend to get clearing, warming, and drying. Okay, so that's what we're going to talk about today. So let's talk about a couple of different ways that you can get these divergent and convergent solutions. First of all, from a directional standpoint, directional divergence would be something like this, where you have air coming along in the flow and then it spreads apart, okay? So that would be directional divergence. And then directional convergence is exactly the opposite, where you have winds coming along and then they start to converge or come together. So those are the two ways you can get divergence and convergence from a directional standpoint. Then you also have the speed component entering into all of this. So speed divergence would be if you have an area of weaker winds embarking on an area of stronger winds. So the air in effect here is spreading apart, and so you get divergence due to differences in speed. And then speed convergence would be exactly the opposite, where you have an area of strong winds embarking on an area of weaker winds. You have an accumulation of mass in here, and so that is referred to as speed convergence. Okay, so let's get into the math just a little bit, hopefully not too much here. First of all, there are three components to the wind, okay? The U component is the total wind, or the component of the total wind that runs from west to east. So if you have a wind blowing from the west toward the east, the U component of the wind is positive. If it's blowing from east to west, the U component of the wind is negative. The V component of the wind is the component that goes from south to north, okay? So a south wind would be a positive V component, a north wind would be a negative V component. And for those of you that don't like the cold, that should be easy to remember, is that if you have a north wind, it's negative, and that means you don't like it. All right. And then finally, the W component, which is the up-down component of the wind, runs from the surface up. Okay, so upward vertical motion would be a positive W component. Negative vertical motion would be a sinking motion, or a negative W component. Okay, so fortunately, total mass in the atmosphere is conserved. It cannot be created or destroyed. The total mass has to remain the same. And so we have what we call in meteorology the continuity equation, what we call the mass continuity equation. And here is the actual equation. It's the change in the U component of the wind along the x-axis. So imagine you had a 20-mile-an-hour wind from the west, and then just east of there you had a 10-mile-an-hour wind from the west, okay? So you have speed convergence going on, and so you're looking at how the U component is changing along the x-axis. Then you have the change in the V component along the y-axis, okay? And the change in the up-down component of the wind with respect to height, okay? All of that has to be equal to 0. Well, it turns out the first 2/3 of that equation, this part right in here, basically is the total horizontal divergence, okay? It's the divergence along the x-axis and the divergence along the y-axis, and so those two terms added are horizontal divergence. So if we solve the equation for the dw dz, which is how the vertical motion changes with respect to height, what we end up with is the dw dz is equal to minus the horizontal divergence. Well, what's the opposite of divergence? It's convergence, okay? So dw dz is equal to horizontal convergence, which means if the air is coming together, then the vertical motion is going to increase with height, okay? If, for whatever reason, you have divergence, okay, horizontal divergence, then the vertical motion is going to decrease with height, okay? Is this making a little bit of sense? All right, so let's look at this from a bottom line standpoint. Horizontal convergence causes the vertical motion to increase as you go up, and horizontal divergence causes the vertical motion to decrease as you go up. So let's look at this graphically. Supposing we had a column of air, you're sitting right here, and there's divergence at all levels of the atmosphere, which means all the mass is being removed. Well, that would not be a good thing, okay, because the air would basically go away and you wouldn't be able to breathe, okay? Fortunately, in the atmosphere, we have a little bit of a compensatory scenario here, where in the upper levels of the atmosphere, just hypothetically, we're going to say we have divergence, and in the lower part of the atmosphere, we are going to say that we have convergence, okay? And right in between those two is what we call the level of non-divergence, okay? And one of the reasons that the 500 millibar chart was used early on and continues to be used to this day is that we're very interested in how the amount of vorticity or spin in the atmosphere is going to change. Well, it can change due to convergence and divergence, but if you're at the level of non-divergence, there is neither of those, okay? So that way you don't have to worry about how the vorticity is going to change with respect to a certain wind pattern. You can simply look at how it's going to change for other reasons, but you can leave out that particular reason. So that simplifies things a little bit. That's why the 500 millibar level is looked at so much. Okay, let's move on ahead here. And this is the last slide. I know you're glad to hear that. So this is a vertical profile of what I just showed you, where divergence is along the x-axis, okay? Minus values indicate convergence, positive values indicate divergence. So we have low-level convergence, upper-level divergence, and notice that the maximum value of the divergence is stronger than the most negative value of the convergence, which means you're removing overall mass from the column. You're not getting rid of the air altogether, but you're removing more mass up here than you're accumulating down here. And so as a result, you have upward motion, okay? And the maximum vertical motion is going to occur at the level of non-divergence. Remember, convergence causes the vertical motion to increase with height, divergence causes it to decrease with height. So what we end up with is there's basically zero vertical motion right at the ground, but that vertical motion increases until you get up to the level of non-divergence. That's where it reaches its maximum velocity upward. And then when you have divergence aloft, then it begins to decrease. And when you get to the top of the troposphere, it's basically zero, okay? So bottom line is the vertical motion is strongest either up or down at the level of non-divergence, which is generally around 500 millibars, give or take a little bit. All right, I hope that made a little bit of sense. That is bonus weather video number 2 for this week. Number 3 will be coming up on Friday, and the next daily update, of course, coming up tomorrow. So I hope you have a great rest of your Wednesday evening, what very little is left of it. And if you don't watch this till tomorrow, I hope you're having a great Thursday, and we'll talk to you either tomorrow or later today, depending on when you see this. All right, take care, everybody. We'll talk to you soon. See ya.